Is agent memory just RAG with extra steps? That is the top comment under almost every memory launch, and it is a fair question. I am going to agree with it for the first half of this video, and then show you the part where it stops being true. First, who is talking? We build Mnemoverse, a memory layer for AI agents that connects over MCP. So we are a vendor in the category this video is about, and you should weigh everything I say accordingly. I am going to open other people's source code and ours, and you can check every file yourself. Chapter 9 is where I tell you when not to buy a memory layer at all, from us or from anyone. Start with what RAG actually does at query time, because the version our category argues against is not the real one. In the original paper, retrieval is a bi-encoder over a document index, resolved as a maximum inner product search. Take the top K passages, concatenate them with the input, generate. That is it. And here is the line that our own industry keeps forgetting. The authors write that we can update RAG's world knowledge by simply replacing its non-parametric memory. The index is swappable at test time with no retraining, so RAG is not frozen. Every pitch that begins with a static, frozen retrieval system is arguing with something that was never in the paper. Now the other side. What does a memory layer do at query time? This is mem zero shipping search function. It embeds the query. It overfetches from the vector store 4 times the requested limit, or 60, whichever is larger. It runs a keyword search alongside. It fuses the 2 scores. It optionally reranks. Then it filters out anything expired. Embed, overfetch, keyword, fuse, rerank. That is a textbook hybrid retrieval pipeline. There is no second mechanism hiding behind it. LangGraph is more explicit still. Long-term memory, there is JSON documents under a namespace and a key, and the docstring says plainly that without a configured vector index, the store will not support vector search at all. And then there is the one that should end the argument. Anthropic ships a first-party memory tool with no embeddings, no retrieval scoring, and no decay of any kind. It is 6 file commands, and the documentation says the tool operates client-side, that Claude requests file operations, and your application executes them. A memory tool from the company that makes the model, and it is a file system. So here is the concession, and I want to say it plainly because our category usually does not. For these systems, at read time, there is no distinct memory mechanism. The skeptic is right. If you drew 2 different diagrams for the read path, one of them was fiction. Now the part where it stops being true. The difference is not on the red path. It is on the right path, and there it is real. 3 things happen when a memory layer writes that do not happen when you index a document. A model decides whether the thing is worth storing at all. The new item is reconciled against what is already there before it lands. And the stored unit can carry a validity interval that is separate from when you learned it. That third one is worth seeing. In Graffiti, which is Zepp's engine and Zepp is a competitor of ours, every edge carries 4 timestamps. When it was created, when it expired, when the fact became true, and when it stopped being true. When a new fact contradicts an old one, the system does not delete the old edge. It sets the invalid timestamp to the moment the new fact became true. The old fact stays, marked as no longer current. Compare that with the alternatives. Mem0 open source expiry hides expired memories from reads rather than deleting them, which is demotion, not forgetting. And AMEM rewrites its neighboring memories with a language model when a new one arrives, so the original is gone and nothing tells you it changed. At this point, the sharpest objection in the thread is, so what? I will just add timestamps to my metadata. You can. Nothing stops you building by temporal validity on a vector store with metadata filters. That is real and it works. The difference is where the reconciliation code lives and who maintains it. With metadata, contradiction handling happens at query time in your application, written by you, and it grows every time a new kind of conflict appears. In a memory layer, it happens once, at write time, in code you did not write. That is a weaker claim than our industry usually makes. It is also the true one. The distinction is not what is possible. It is what is amortized and who is on the hook for it. There is one asymmetry that survives all of this, and everything after this point is a consequence of it. A memory layer retrieves from a corpus it wrote itself. Extraction writes the memories, retrieval reads what extraction wrote, and the output feeds the next extraction. It is a closed loop. A RAG corpus is not in that loop. Your documents were authored somewhere else, and the system only reads them. It cannot corrupt its own source. Once memory writes its own corpus, its extraction errors become its retrieval corpus. And that explains the complaint you see under every one of these launches. It remembers the wrong details and applies them in the wrong places. So why does an agent remember the wrong things? The answer reframes the whole problem. Everyone in this category talks about eviction, about what to throw away. But a paper from July, Consistency Gate, states the harder problem directly. Existing memory management addresses retrieval and capacity, not write time correctness. And it says this cannot be solved by utility or recency-based criteria because a hallucinated fact written at one step persists as a false premise for every step after it. They call it memory contamination. The hard decision is admission, not eviction. What gets in? And now the part that made me uncomfortable when I checked it. In every reinforcement scheme I opened, retrieval is what keeps a memory alive. Generative agents updates a memory's last access time every time it is returned. Memory bank increases a memory's strength and resets its clock whenever it is recalled, in their words, so that a recalled item persists longer. LangGraph store refreshes an item's time to live on read, and that is the default. Put those together. A wrong fact that keeps getting retrieved is protected by the exact signal that was supposed to prune it. The mechanism meant to forget the useless is the mechanism keeping the wrong thing alive. I will say this about our own system too, because it is worse in a specific way. Our write gate scores how novel a new memory is against the nearest existing one. A correction is usually phrased almost exactly like the thing it corrects, so it scores as a near duplicate and gets rejected, and the stale fact survives as the only record. That is written in our own changelog as a known defect. It is our problem in public, and it is the same problem this chapter is about. Which brings me to the most useful thing I can show you. Papers and shipping code do not agree, and you can check this yourself in 20 minutes. Mem0 paper describes an update phase with 4 operations: add, update, delete, and no op. In the library at the commit I pinned, that code path is dead. The prompts exist, the tests reference them, and the production write path never calls them. It appends and links instead. The graph variant from the paper is not in the open source Python package at all, and passing the decay flag raises an error. Generative agents is the sharper example. The paper says the 3 retrieval weights are all set to 1. The code multiplies by half, 3 and 2, with the equal weights commented out directly above and an author note saying they should probably be learned. And its recency term decays over position in a sorted list, not over elapsed hours. None of this makes the papers dishonest. Research code moves, but if you are choosing a memory system by reading papers, you are choosing something that may not be running. So, when do you not need a memory layer at all? Below roughly 150 conversations per user, the evidence points at doing nothing clever. ConvoMem, which is academic and not from a memory vendor, finds that simple full-context methods beat retrieval-based memory systems on its hardest cases, and puts the crossover around there. Leta, a competitor of ours, reports that an agent given nothing but file system tools over a plain transcript scored above Mem's 0 published result, and argues that current memory benchmarks may not be very meaningful. Their line is worth repeating. Memory is more about how agents manage context than about the exact retrieval mechanism. On benchmarks generally, be suspicious of all of us. Every vendor reports its lead on a benchmark it chose and disputes the other's methodology rather than reproducing it. That includes us. You will notice there is not a single performance number in this video. Ours are frozen until our own measurement harness ships, and I am not going to quote anyone else's to fill the gap. 2 more reasons to be careful, and both apply to us. Writable memory that persists across sessions is a different security surface from a read-only corpus, and the research is explicit that it cannot be fixed at retrieval time alone. And erasure is not solved by anyone here. If a fact has been summarized, consolidated, and embedded, deleting the original does not obviously delete its descendants. And the honest state of the field, a survey from March lists learned forgetting as an open problem. The repeated compaction that agents actually perform is almost never measured. Nobody knows yet. So here is what to do instead of trusting anyone's diagram, including mine. 3 checks and they work on any vendor. Open the read path and see whether it differs from hybrid retrieval. Store a fact, then contradict it, and watch what happens to the original. Then submit a correction and see whether the system accepts it or whether it decides the correction is a duplicate. That third one is where we fail today. Run it on us. The written version of this, with every source linked and every file path, is in the description.